Hello, everyone. My name is Stefanie Pichler. I'm a master's student at Universität Leoben, working at the corrosion group. And today I would like to present you one of our research topics about the applicability of API 5 CT steels for hydrogen underground storage. The experiments of these projects were conducted by Bernd Loder, a former PhD student of our group who already graduated, and the project was supervised by Professor Gregor Mori. I want to start my presentation by giving a short introduction, then talk about methodology and experimental program, followed by some results, sum up in the end, and draw some conclusions. So starting with introduction, I just want to briefly show you all of our industrial partners. We are working together on projects regarding hydrogen transport and storage. And as you can see from the map, they are spread all over Europe. So now I want to explain a little bit what is the difference of a pipeline and casing and tubings. Pipelines are used or will be used for hydrogen transport, whereas casing and tubings are used for hydrogen underground storage. Condition-wise, pipelines are exposed to pressures of around 70 bar pure hydrogen gas, whereas casings and tubings are exposed to pressures up to 300 bar. Additionally, in underground storage facilities such as depleted gas reservoirs, aquifers, and salt caverns, hydrogen is prone to contamination due to remaining cushion gas. And as already mentioned in previous talk, formation water with different salinities from brine. So due to these different conditions, for pipelines, ferritic steels are used, and for casing and tubings, ferritic or quenched and tempered steel with a higher strength are more suitable. And casing and tubings are connected via threads and not welded. So now I want to start introduction. In literature, they reported the investigation of 4 different carbon steels, ferritic carbon steels. They performed SSRT in high pressure hydrogen environment at ambient temperature. And comparing inert tests with environmental tests, they found that embrittlement only occurs once tensile strength is reached. So substantial plasticization is necessary to induce hydrogen embrittlement. Another finding of their study is that with increasing volume fraction of perlite, the relative reduction in area decreases and the hydrogen-assisted surface cracking increases. The previous study is in good agreement with another study. They also performed SSRT on carbon steels, ferritic steels, as well as tempered martensite. Again, performed SSRT in high pressure hydrogen environment, different temperatures, and they also found that cracking occurs near UTS. Another method to study hydrogen embrittlement would be fracture mechanics, based on Paris law, which evaluates the crack growth rate of a fatigue crack. Studies show that cyclic crack progression increases in hydrogen atmosphere by a power of 10. And for the last part, I want to explain ripple load tests. This study is actually a cooperation of the French Corrosion Institute and our group, where the ripple load tests were conducted at the French Corrosion Institute. And ripple load tests simulate storage processes where the samples are loaded up to 100% specified minimum yield strength. And then the load is reduced to about 80% specified minimum yield strength. It's in the low cycle fatigue regions with 200 to 300 cycles in total. They investigated different carbon steels, and the results show that no cracks occurred. However, in the presence of 1 bar H2S and a lot of salt water, about 200 gram per liter, and incipient local attack, pitting could be noticed, which of course could lead over several cycles to cracks. So now I want to talk a little bit about methodology, more specifically about autoclave testing, constant load tests. For autoclave testing, small tensile specimens are loaded with a spring up to 90% specified minimum yield strength, and then the tensile specimen, the loaded one, as well as another small sample to evaluate hydrogen content after testing or put into the autoclave and into the heating chamber. The tests are conducted either in dry condition or immersed in electrolyte with different salinities or immersed in electrolyte and gas. And to guarantee the alternating immersion of the specimens are rotated with one round per minute inside the heating chamber. And the test duration is 720 hours, which corresponds to 30 days. Now I would like to go on with experimental program. In this project, the investigated materials were different carbon steels, as well as corrosion-resistant alloys. And the materials were tested using high pressure, high temperature autoclave testing, as well as hydrogen analysis with TDS. The test conditions, the tests were done with different gas compositions, including pure hydrogen at 120 bar with or without the presence of CO2 and H2S or both of them. And the tests were conducted at room temperature and 120 degrees. So now I want to show a few selected results. And first I want to start with the welded carbon steel J55. As we can see in this diagram, it shows the hydrogen uptake after autoclave testing in pure hydrogen at 120 bar. On the left side, you can see the results after testing at room temperature, and on the right side, you can see the results after testing at 120 degrees. The white bar on the far left always shows the dry hydrogen content, and the other bars show the hydrogen content after the testing in electrolyte with different salinities. And as you can see from the diagram, there was very low hydrogen uptake at room temperature and just a very slight increase at elevated temperatures. So when we add now 15 bar CO2, we can see a slight increase in hydrogen content. This is due to CO2 reducing the pH value to around 5, and however, there's still no significant increase. However, when we now add 1 bar H2S, especially at room temperature, we can for the first time see a more significant increase compared to previous conditions, and this is due to H2S reducing the pH down to about 3, and also H2S working as a recombination poison regarding hydrogen uptake. However, at elevated temperatures, H2S leads to formation of an iron sulfide layer, which prevents hydrogen uptake as it is quite dense. Okay, now I want to go on with the stainless steel 316L. Again, on the diagram, we can see hydrogen uptake after autoclave testing. The white bar shows the content after testing in dry condition, and the blue bars after testing in electrolyte. And what we can immediately notice is a higher hydrogen content in dry condition compared to previous material. All these tests were conducted at room temperature. And what we can see after adding the electrolyte, regardless of the addition of CO2 or H2S, hydrogen content only increases about 1.5 ppm. So not significantly, and that can also be observed very nicely from the SCM image on the right, where we see that there is no surface attack, and also for this alloy, no cracking occurred. The next material I want to focus on is the carbon steel P110. Again, the same procedure, the hydrogen content after autoclave testing in dry condition versus tested in electrolyte at different gas compositions. And we have a very low hydrogen content in dry condition. And when adding the electrolyte, we can only observe an increase in hydrogen content in the presence of H2S. And this can be observed very nicely here in the SCM image on the right. We can see a local attack. And this, of course, could become critical over time in loaded condition. So it can be said that this material is not really resistant to acid gas. For summary, I want to show you a quick overview over all the materials tested throughout the whole project and how they performed. It can be said that only 2 materials tested in the project really failed the test, which was the duplex steel and quenched material. All the other materials are well applicable, or at least applicable to a certain extent. What we have seen on previous slide for P110, it is only applicable in case when there is no H2S present at room temperature. Now I want to draw some conclusions. To conclude, it can be said that the carbon steels are in general applicable for hydrogen storage, with the exception of L80. There are some limits regarding H2S and another exception of P110 with strong limits regarding H2S. And corrosion-resistant alloys are also well applicable for hydrogen storage, with one exception of the duplex steel, which failed the test and is therefore not applicable for hydrogen storage. Okay, now I'm at the end of my presentation. Thank you for your attention.